There we are. Okay. In case you went too close to a magnet during the break, new stars spend most of the rest of their lives on the main sequence, converting hydrogen into helium. Now this is about red dwarfs. How long do they do that? 20 billion years. So the thermonuclear fusion will finally stop after 20 billion years. Then they slowly cool down to darkness and become a black dwarf. And remember, the universe isn't old enough for that to have happened yet. So all the red dwarfs are still around. Now we're on solar-type stars. What will happen to the sun at the end? That should have some interest to us if we kind of ignore the time scale. After about 10% of the hydrogen is used up, the fusion reaction stops. You might think it would use up the whole thing, but as that core of helium builds up and the shell of where the hydrogen converts to helium moves farther and farther out, the pressure and temperature decrease, and it's not enough to cause the reaction to occur anymore. So after about 10% of it's gone, then that's the end of the line for stars like the sun. Core mainly contains helium and a few other heavier elements, 20 million degrees Kelvin. That's why this reaction takes place in the first place, because it's so crowded and hot and everything moving very fast. So that eventually stops. But then a remarkable thing occurs. It's sort of like you built a fire in your fireplace and all the logs burned down and there's nothing left but ashes. And then all of a sudden the ashes caught fire and a new fire starts from the ashes. It's brighter and hotter than the logs in the first place. That's what happens in the center of the sun. The helium that was produced in the first phase of the sun's life while it was on the main sequence, those atoms start fusing together. And the reaction for that we refer to as the triple alpha process. Now, these are some of the strangest looking atomic nuclei you'll ever see, but they're kind of a diagram more than anything. Here's the the helium nucleus. You are aware that a helium nucleus is the same as an alpha particle from radioactivity days and so on. Same thing. So two of those fuse together to form a beryllium nucleus. And then that beryllium nucleus reacts with another alpha particle or helium nucleus to form a carbon atom. And each one of those steps gives off energy. You add all the reactions together, 3 helium nuclei give you a carbon-12 atom and gamma radiation, which is how the energy is carried off. That's why it's called the triple alpha process, because 3 helium nuclei join together. This doesn't stop either. Once we get a lot of carbon formed, then that starts reacting and combining, and heavier elements are built up, and every one of those steps gives off energy. Those fusion reactions always give off energy as long as we are building up towards the element iron. That's the magic element. If you're fusing lighter elements to get towards iron, energy is always given off. I guess this is as good a time as any to mention it. When the opposite occurs, if you take very heavy elements like uranium and you split them up, I think you had a question about that earlier, in the fission reaction. That also gives off energy because say a uranium atom splits into, say, a barium and a krypton atom, which is typical in an atomic bomb. When that happens, the barium and krypton together weigh a little less than the uranium atom did to start with. And that missing mass is also converted into energy. So if we're going down the periodic table from the left side, hydrogen, helium, lithium, and on down towards iron, that gives off energy. If we're up on the high elements on the right side, uranium on down towards iron, that gives off energy. It's when you cross the iron and go the other way that everything changes. So, more energy. Now, instead of a few billion degrees, we're now about 1 trillion degrees Kelvin in the center of the star. That causes the star to get a whole lot bigger. Now, we're talking about the sun now. It might be 100, 200 times bigger than it is right now. Here's the structure inside. Here's the surface outside, nearly as big as the orbit of Mars. And within the center, we have where the hydrogen isn't being converted into helium anymore. Here's the helium, where that's getting converted into carbon. And that's what's going on right in the very center here of a red giant star.
And Mercury came into Earth.
Coming right up. Yes, yes. They have to spiral in first. That takes a little while. But that, since the surface is now so far from the center, it's cooled way down. So it's now red. So hence a red giant. It's enormous, but the temperature in the center is 1 trillion degrees, but the surface only a few thousand, so it's glowing red. So it's cooler, but since it's so much bigger, that increases the luminosity and takes it up towards the upper right-hand corner of the HR diagram. So up because it's more luminous, to the right because it's cooler. When the sun becomes a red giant, the inner planets will, as Rick pointed out, drastically change. The atmospheres get stripped away. Remember when we were talking about the formation of the solar system? Hydrogen and helium got stripped away as soon as the sun started cooking. But then this is going to take care of practically everything else except the rocks. Anything volatile is going to be boiled away. No life possible under those conditions. Unless we figured out some other way to do it before then. That will be the end of life on Earth as we know it. And the Earth itself, while it won't be inside the sun, will probably be glowing dull red like the sun itself, and the sun will occupy about 75 degrees in the sky. Quick review, how big is it now? Half a degree. 75 degrees, 150 times bigger when it becomes a red giant. So this is the way things will look 5 billion years from now after the sun becomes a red giant. Mercury and Venus will be inside it and will spiral in towards the center. And here's the interesting thing about this, or one of the interesting things about it, is that expansion to the red giant takes place so fast that the outer surface of the star loses its equilibrium balance with the gravity and just keeps on going. When the star expands to be a red giant, the outer surface layers are cast off and form a shell around the star. And we call that, here's another misnomer, a planetary nebula. It has nothing to do with planets, except that they look a little bit like planets in the early telescopes. So we'll see some pictures of those, but you know, the Ring Nebula is a planetary nebula. It doesn't have anything to do with a planet. Here's some examples: the Dumbbell Nebula and Vulpecula, Ring Nebula. We looked at both of those at Village Creek. Here's the Dumbbell. There's the star that did it all, a solar-type star that went through its time on the main sequence, expanded to be a red giant, sent out this spherical, more or less, shell of gases around itself. Here's one, the Ring Nebula, everybody's favorite because it's so easy to find right between two stars. And there's the star that did that. And it's a little older one. You can see his shell has had a chance to open up a little bit since it happened. Okay, now the red giant star starts to contract again and moves across the Hertzsprung-Russell diagram pretty much straight across to the left. It gets hotter and yellower instead of red, and maintains about the same luminosity. So it's kind of sailing across the top of the HR diagram. And while it's doing that, it becomes unstable and starts to pulsate both in brightness and color. Goes through a period of oscillations that might be days or weeks typically in length. And these are Cepheid variables. We'll have a lot more to say about those and measuring the distance scale in the universe in February when we finish up with Chapter 12. Here's kind of how that works. A variable star, and I use the term intrinsic variable, which means the star itself is doing it, unlike an eclipsing binary where one star moves around the other and one's either in front of the other or side by side, and that makes them appear to vary. That's not what we're talking about here. One where an actual star pulsates has a valve-like principle. When the star is smaller, it's brighter and hotter. but the outer layers are opaque to radiation coming from the center. So that makes it expand and cool down and get dimmer. However, when it does that, the outer part of that star is now transparent to the radiation coming from the center, so it can escape. And it just cycles and does that over and over. Picture blowing up a balloon, if you will, that when it's small, it has, its balloons are porous. They have holes all through them, but they're small when the balloon is deflated. And you start blowing into it, the balloon will expand. But when the balloon gets really big, the holes get bigger too, and more of the air escapes, and it will start to collapse down, but then the holes close up, and it'll be more airtight, so when you blow into it, it gets bigger again. So it cycles back and forth like that, and that's how these variable stars work. And we'll see more about them in a couple of months. Eventually, it gets over being unstable, still stays white hot, but gets smaller and smaller because it goes down the left side of the Hertzsprung-Russell diagram and becomes a white dwarf, like Sirius-B, the companion to Sirius-A, the brightest star in the sky. Comparable in size to the Earth, but density is ridiculous, 6,000 tons per cubic foot, because about 60% of the star is still there, but it's only about the size of the Earth instead of 100 times the diameter of the Earth. So it's really compressed. And eventually it will cool off. There's no reactions going on in the center anymore. And eventually it'll cool off and become a black dwarf, but that probably hasn't happened yet. The universe isn't old enough for that to have occurred. Here's all of that. Here's a solar-type star on the main sequence. Here it's turned into the red giant, sent out a planetary nebula, gotten hotter as it moves across, becomes unstable. Here's the variable phase. It wouldn't have killed them to put about another inch on this diagram here. So as it comes across here, then it goes back down through here, getting smaller and smaller, less luminous, but still hot as it becomes a white dwarf star. So that's what will happen to the sun. And we can get a pre-picture of that by looking at planetary nebulae. There's a rough indication of the size comparison. Here's the Owl Nebula in Ursa Major, right below the bowl of the Big Dipper. We'll be seeing that during the springtime. There's the star that did it, solar-type star, red giant, sent this disk out, then went through a variable phase. Now it's a white dwarf. And just some eye candy here. Here's the Cat's Eye Nebula in Draco, and it must have been spinning in a fancy way to send out the shell around it like that. And here's the biggest one of all. It's about the size of the moon in the sky, the Helix Nebula in Aquarius. We'll be seeing that at our next non-rained out observing sessions. It's very dim. It's the closest and biggest of all the planetary nebula, and that's the star that did it.
Now, they don't always blow off their shell in a perfect sphere.
Not always. Right. If they're spinning or tumbling, or if there's a companion star, that can interrupt all of that, and it's like it's gone into a mixer or something like that. It comes out looking totally confused.
Some of them come out and blow.
Yes, yes. Yeah, we've had a whole talk once just on planetary nebulae, so, and all the different forms and the causes for them. This is the streamlined version, believe it or not. Okay, now for slightly bigger stars like Sirius that are maybe 3 times the mass of the sun. They do pretty much the same thing except faster, not as many billions of years, like 1 billion instead of 10. 25 times as luminous as the sun, and so it can only last about 1 billion years on the main sequence, and like 10 for the sun. After it leaves the main sequence, it goes up to the upper right corner as well, becomes a red giant, sends out a planetary nebula, becomes an unstable variable, and then winds up as a white dwarf. So pretty much the same except faster. Here's where the fun comes in. The really big stars, the blue giants at the upper left end of the main sequence, like Rigel or Spica, they only last about 4 million years on the main sequence, burning hydrogen into helium. When the helium starts to burn, then the star becomes a red supergiant. Same principle as a red giant, but a lot bigger. Antares, Betelgeuse, about 350 million miles in diameter, which is larger than the orbit of Mars. So these are the largest known stars. The ones that were blue giants and now red giants. The ones you see when you look at the double cluster in Perseus, you see the blue ones that are still on the main sequence. You see the red supergiants. And they're not in the upper right corner of the telescope field either, just the Hertzsprung-Russell diagram. They're scattered throughout the field of view. Eventually, the thermonuclear fusion can no longer produce energy. I think I referred to that earlier when I said that iron, if you're heading towards iron by building up smaller elements, that gives off energy, and that balances gravity. In an atomic bomb, if you're breaking down heavier elements into smaller ones, still going towards iron, that gives off energy. But if the core of a star has already converted a lot of elements to iron, it's going to keep going. The pressure and temperature are there. It's going to start making heavier elements, but there's a huge difference. It doesn't give off energy anymore to balance the gravity. In fact, it's starting to absorb energy. After a couple of diagrams, we'll see what happens there. It's like a cross-section of an onion. All the different things that are going on or have gone on in the core of a red supergiant star, nearly as big as the orbit of Jupiter. You can see all the different layers of elements that are formed in the iron core. It goes past that, and here's what it's doing on the main sequence. One that's 5 times as massive as the sun goes up here, becomes a red supergiant. So does a 10 solar mass one. It doesn't show what happens after that. Here's something hard to believe. Once the star starts making elements heavier than iron, the energy is used up so rapidly that the star starts to collapse, only taking a few hours or maybe even less. A fraction of a day, actually. Because the energy that normally balances gravity is now got a minus sign in front of it. The star is putting out negative energy, absorbing energy, and it's heading towards the collapse the same way the gravity is. They're both pulling in the same way. There's no balance anymore. And after it collapses, then the core bounces back out and collides with all the outer stuff that's just now getting the message that it's collapsing. It's falling in while the core is bouncing back out through it. And that leads to what we call a Type II Supernova explosion. Here's a little timetable. I'm going to leave out the temperatures and the densities here, but that's kind of interesting to look at. But how long does this take? Say a 25 solar mass star on the main sequence burning hydrogen for 7 million years. Helium burning 700,000 years. Carbon burning 600. Neon 1 year. Oxygen 6 months. Silicon 1 day. The core collapse 1/4 of a second before the star collapses. And then the rebound is in milliseconds. And then when it explodes and moves out through the outer part of the star, that might take as long as 10 seconds. So if you thought stellar evolution was a long, slow process, it is getting up to here. But at the very end, it all happens extremely fast. Here's a diagram for it. Here's a red supergiant like Antares or Betelgeuse. And here's the core that's got iron in it, and it starts making heavier elements, so the core starts to collapse. And it goes in and bounces off of itself and starts back out again. And meanwhile, it hits the other material it's falling in. So probably about 1/3 of the way out from the center, maybe halfway, a tremendous explosion occurs where the infalling material hits the outgoing material, and the pressure and temperature there are so great that all the elements in the periodic table are synthesized during that 10-second period. Because all the, it takes energy, but good grief, you got energy to spare when you've got a Type II supernova going on. So all of this energy that had been the star is now being converted into making heavy elements that then get blown out into the universe.
How do you make gold?
Among other things, yeah. This doesn't happen all that often. Every few hundred years in a typical galaxy. Here's some of the ones that have been recorded. The 1054, the Crab Nebula one, we'll see that in a few minutes. Tycho's star, which got him interested, and Kepler's star got him interested. It's a good thing both of those happened, but as you can see, we're overdue for one. Let's just hope it isn't particularly close to us, but we are overdue for a supernova in the Milky Way galaxy. Sometimes if we see a supernova in another galaxy, it's so bright that it outshines all the other stars in that galaxy put together. Sometimes galaxies have been discovered that way. You'll see a little star there, and you look at it with a telescope, oh, there's a whole galaxy there that we never noticed before, because nothing was particularly bright until one of its stars blew up. Here's one in the Big Dipper, M81. What's that up there? M82. You've seen those in the same field of view in the telescope. Here's before it happened, and here is when there was a supernova in M81 back in 1993. Seems like only yesterday to me, but a lot of you weren't even born then. So.
How long did that shine for?
Weeks. Okay. Yeah. And then they can trace it back down, but you kind of like to catch it on the way up because you learn a lot more that way. So you always have these supernova patrols that people have photoelectric photometry and look for anything unusual, and then used to send out telegrams. Now they have better ways of alerting everybody for that. Here's the one, 1987. I said we were overdue for one in the Milky Way because this wasn't exactly the Milky Way. This was in the Large Magellanic Cloud, one of the satellite galaxies of the Milky Way. In 1987, this was the progenitor star that did it all. And here's what it looked like visible to the naked eye when it exploded. And that was the most studied supernova in all history, was in 1987. And it was in as nearby a galaxy as you can get without it being in our galaxies, one of our satellites, Magellanic Cloud. This is the Tarantula Nebula, by the way, which is bigger and brighter than the Orion Nebula, and it is really a sight to see. You can see it out of the corner of your eye and jerk your head towards it when you go outside in the winter in the southern hemisphere. Amazing sight. Here's the one that was, before that one, was the most studied supernova, the Crab Nebula story. 4th of July, appropriately, in 1054 AD, Chinese astronomers noticed a guest star in the part of the sky that we now call Taurus. Who knows what we would have called it, an invading alien or something? They called it a guest star. So that kind of tells you a little bit about that culture. Star got so bright, -6 magnitude, that it outshone Venus, which is typically -4. You could see it in broad daylight for several weeks. And while it was still visible, they carefully noted the position among the stars. This, of course, is before telescopes. And after the invention of the telescope, we look back at that same place in the sky, and this is what you see there. This is M1, the one that got Messier started on his list so he wouldn't mistake it for a comet. So this was the led off his list, M1, the Crab Nebula in Taurus. The star that did it all is still visible. It's the dimmer of the two, kind of near the center. Now the shock waves, as we've seen, go out through the exploding star when the explosion takes place and synthesizes all the heavy elements in the periodic table, and probably then some. Here's another supernova remnant in the southern constellation of Vela, the Sails, and we can see the wreckage of that star. Naturally, there's no way to figure out where the original star was and all that mess. It's right in the middle of the Milky Way. And here's my favorite, the Veil Nebula in Cygnus, which they call the Vial Nebula in Australia. And it's kind of in sections. You can look at different parts of it. It's so big you can't get it all in the one eyepiece field, really. So all the different heavy elements spreading out through space after the explosion of that star. And they mix with the dark nebulae and become incorporated into a new generation of stars. In other words, they're recycled. The old blown up stars that make the heavy elements is the last thing they do in the last 10 seconds of their lives, seed the new nebulae that are forming into new stars, new solar systems, and that's how the contamination of the 2% other gets into the dark nebulae that are making new stars. Here's another little piece of the Vial Nebula expanding, and here's another around 52 Cygni. This is the Witch's Broom area. Some of these new stars probably have planets, and they're contaminated with heavy elements, like iron, silicon, carbon. To astronomer, anything past lithium is a heavy element. They're kind of strange like that. So they're contaminated with all those elements. Like the Horsehead Nebula, you know it's got these other elements in it because it's still a dark nebula. It's still forming, hasn't even started forming stars yet, but when it does, they will have all of those elements in it. The Earth, we've already seen the lighter elements have been driven off by the sun. Remember, the Earth used to be 95% hydrogen, 3% helium, 2% other. Once the sun got cranked up, the 95 and 3 got gone, and all that's left is the 2% other. Well, you may think there's a lot of hydrogen there because of all the water in the oceans, right? Well, to scale, the thickness of the oceans is less than the skin of an apple by scale comparison. So it looks like there's a lot of water there, but it's the thinnest of layers. And everything here used to be part of a star, including us. The elements that make up our bodies, the rings on our fingers, the wood in the trees and the formica, whatever that is, and the desktops, everything here came from supernova explosions several generations of stars before the sun and the rest of the solar system were formed. We saw some pictures of new solar systems forming back in July. They weren't forming back in July, we saw them in July, of these proplids, protoplanetary disks, new solar systems being formed. And these are mainly in Orion. Here's one in Taurus. It's just like the formation of our own solar system with the sun in the middle and the rings behind forming into planets. So it's all a big recycling thing. The final thing, that shock wave that occurs in a supernova exploding, so far we've talked about what it does to the outer part of the star, making all the heavy elements and then blowing them throughout the universe. That shock wave also is directed inwards as well. In fact, even more strongly. It hadn't got anywhere to go. So the shock wave directed towards the center is enough to cause whatever elements are there. We're not talking about heavy elements anymore. Any element that's there is made up of either neutrons already or protons and electrons. Well, the protons and electrons get smushed together to form neutrons. So every atom in the thing, no matter what it was, iron, silicon, carbon, hydrogen, all of those are now neutrons. Well, and neutrinos come out of a supernova explosion as well. Neutrons are neutral, zero charge, mass of 1. So they don't repel each other, so they get very close to each other like touching. So the 40 or 50% that's still left of a star then actually becomes just a big ball of neutrons, only a few miles in diameter. So what was once a red supergiant star is now smaller than Memphis, but maybe with a good part of the mass, 40, 50%, still there. You could also consider it a very large atom, very small star, very large atom. And this gets just totally ridiculous here, 1 billion tons per cubic inch for the density of a neutron star. If you took one little pinch of it, it would weigh more than all the elephants in the Earth combined.
Elements or elephants?
Elephants.
Okay.
Elephants, yeah. Well, yes, that's right. Elements are made up of elements. It's getting near where I need to wrap this up. Okay, looking at the interior part, we've seen what happens in the outer part, this mango here, and then towards the center, now we're looking at the formation of the neutron star in the center from all that pressure and temperature from the explosion. Stars tend to rotate. They probably all do. But if a big star is rotating slowly, due to the conservation of angular momentum, when it gets down to 10 miles in diameter, it's going to be whirling around at a tremendous rate. And since it's such a high density, it's not likely to fly apart or even get away from spherical. It's just be a spinning ball of neutrons, maybe spinning numerous times per second. If it has hot spots on the surface due to irregularities, it'll send out beams of radiation like a lighthouse. If we happen to be looking at it from the right perspective, this neutron star will appear to flicker on and off. And those were called pulsars because they send out pulses. The first ones discovered were sending out radio waves. That was how it was discovered with a radio telescope in Australia. Jocelyn Bell, a graduate assistant at the time, since gotten her PhD, was analyzing data from the radio telescope and noticed this blip, 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 extremely regular. We had been sending out signals like that, trying to get a response from somewhere else out in space, other civilizations. So they first started calling them LGMs, which stood for Little Green Men, because they sort of halfway thought we were hearing from some other alien civilization. But once it turned out to be a rotating neutron star, it solved a lot of physics, but it ruined a lot of science fiction. Here's the rotating pulsar model for neutron stars. And again, that's the star that did it, right there in the Crab Nebula. That first pulsar was discovered in 1969 in the radio telescope. Later that summer, I went to an Astronomical League convention in Washington, and my roommate was Saul Levy, who was working at the time. He'd graduated from college in Pittsburgh, where I met him, and he was at Kitt Peak. And the rooms were not air conditioned, and it was in August, and we stayed awake all night talking about things like astronomy, and particularly the new pulsars. And they had decided they were going to check the Crab Nebula to see if the star in the middle of it here was actually a pulsar. Because, you know, if it's blinking really, really fast, like the fluorescent lights, you can't see it. So they had to figure out some way to make it visible. I suggested to them, since I'd done some research in that area, is to hook up a photocell to the telescope and run that to an oscilloscope, and then see if you had a little blip at a regular spaced interval. Well, it turns out they didn't do it that way. They did it even more simply and elegantly. They just spun a disc with a hole in it in front of the eyepiece of the telescope to make a strobe effect, and they got it spinning, and there it would come and go and come and go. Saul called me at 3 o'clock in the morning to tell me they had done that, and I was very glad to hear it. A little disappointed they didn't use my idea, but I was glad to hear how it worked out. Here's the pulsar and the neutron star with the stuff orbiting around it. And that's not quite the end. It was back in 1970, 69. But since then, it turns out that a neutron star can collapse further if its mass exceeds 2 or 3 solar masses. The neutrons are not strong enough to support the gravity that's trying to mash them together. We call that support that it has neutron degeneracy. And if you have too much mass there, the neutrons will collapse to what? Well, there isn't anything farther down the line. So it goes to a point, a singularity. So under the intense pressure, the volume goes to 0, a singularity, a point in space. You calculate the density, it's whatever mass it has divided by 0. So this is where some wise guy said that here's where God divided by 0 in the universe, to have something with an infinite density. The escape velocity, remember that from back in the formation of the solar system, The escape velocity, which at the surface of the Earth is 7 miles per second, is greater than the speed of light when you get close to one of these singularities. So its own light can't escape from it anymore, and that's what a black hole is something that's got such a strong gravitational field that the escape velocity is greater than the speed of light, so nothing, no light can come out of it. Now, how big is a black hole? Well, it kind of depends on what is. The black hole itself, the singularity, is a point. It has no dimensions. But how far out does its sphere of influence extend? Well, that depends on how massive it is. There's one point at a distance from it, actually a spherical shell, where the escape velocity is exactly the speed of light. Beyond that, you can actually get up close to it and turn away. Once you get inside that, it's all over. You become part of the black hole, the singularity after that, and all you do is just add to its mass a little bit. So that point of no return is called the Schwarzschild radius, or the event horizon, which is the same thing if it's a non-rotating black hole. We could spend a whole program just on black holes. Depends directly on the mass. If you have a 3 solar mass black hole, which is reasonable after all that star has gone through, there's still 3 solar masses left. It has a radius of 9 kilometers, or about 6 miles. If it's 4 solar masses, then it's 12 kilometers, and so on. It's just directly proportional to the mass. So what would happen if the sun, for some reason, this is science fiction, but if the sun wandered up to this black hole, crossed the point of no return, and became part of it? Well, now it would be 4 solar masses, and it would just have a slightly larger sphere of influence from that point on. If there's a companion star, like a red giant that's expanding and getting too close to it, it's dumping mass into the black hole as well. So that makes it get even more greedy. The more you feed it, the greedier it gets, because it gets bigger. It'd be the ultimate disposal. You had one of those confined under your sink, you wouldn't ever need the garbage truck to come around again. Just everything goes into that forever.
Eventually the sink would go away.
Yes, eventually. Here's a diagram of that. Here's a big red giant star with a star that now has become a black hole, with material getting sucked off of the surface of the red giant, circling around and around and around in what's called the accretion disk. If you've ever tried to land at the Atlanta airport, you'll kind of know what an accretion disk is like. You just go around and around and around and eventually get closer. When it does, when that material gets that close to the black hole, it heats way up because it's getting compressed, and it sends out X-rays above and below the plane. And that's how they're detected. When you can't, of course, see the black hole, but if you see a burst of X-rays coming and it's kind of close to a red giant star, you can be pretty sure there's a black hole there causing the X-ray bursts from its accretion disk. Here.
Somewhere to the Atlanta airport.
Yeah, right. Actually, Hawking has kind of changed his mind on some of that stuff. We'll have to go into that some other time. But, whoops. Here's a slightly more artistic version with the red giant getting pulled into the accretion disk and falling into the black hole. Okay, these last 2 slides just summarize the entire evening. Lightweight stars, like the sun, 10 billion years on the main sequence, start gas and dust, live 10 billion years, turn to a red giant, eject a planetary nebula, and wind up as a white dwarf. Here's one we haven't talked about, and I'm going to spend about 1 minute on this. If a white dwarf star is near a red giant and it dumps material on the surface, if that white dwarf ever gets to be more than 1.4 solar masses, it will just collapse and explode as a type I supernova. That 1.4 solar masses is known as the Chandrasekhar limit. You ever heard of Subrahmanyan Chandrasekhar, one of the greatest astrophysicists of the 20th century? He was, in 1930, he was 20 years old. He came up with this theory while he had gotten a scholarship to go to Cambridge in England, and while he was on the ship from India to England, he worked out the equations for the limit of what a white dwarf star could be, 1.4 solar masses. When he got to England, Arthur Eddington ridiculed him, and it didn't catch on for a very long time, but that's another whole story. But that's another sidetrack. Here is the last thing we were doing. A heavyweight star gets a big chunk of nebula, becomes a blue giant on the upper left of the main sequence, becomes a red supergiant, and explodes as a supernova type II, and either winds up as a supernova remnant like the Crab Nebula with a neutron star in the middle of it, or a black hole with an accretion disk on it. I have one final question for you. What drives this entire process from here down to there?
Gravity.
Gravity causes the nebula to contract, causes the nuclear reactions to occur in the star, which eventually expand it, causes the supernova explosion, and leads either to the neutron star or the black hole. All of that's a direct result of gravity. So what's the moral of the story? As anybody my age knows, gravity always wins out. So that's it. Does anybody have any questions about anything? Anybody still there?